So here we have, to initially, hydrogen and chlorine having a pretty good time, hanging out, then aggressive zinc metal just storms on in, steals away chlorine, which is a metal or a non-metal? Non-metal, to make a salt. And of course hydrogen, this is a balanced equation. Hydrogen sitting in the corner by himself quietly. Is hydrogen a metal or a non-metal? Well, it can act as both. Remember, it can move across the periodic table. It can form covalent bonds or can form ionic bonds. And what's happening here is it is acting as a metal. So, and in a chemical equation, where do we find the metals in a chemical equation? Because they typically form positive cations, they're always in the first position. Hydrogen here acting as a metal, and of course the zinc is a metal. And so that's what you're seeing here is effectively that zinc is bumping the hydrogen out of that location. And why does it do this? Okay. Well, it's quite simply, it is more attractive. You get a more attractive bond is formed between, or zinc is more attractive to chlorine and vice versa than hydrogen is. So it will displace the hydrogen in that particular thing. And that's what we're going to have a look at, reactivity of metals, and why they do this. Okay, those are your key learning intentions there. You do get a table in the exam. Yes. So you're not expected to memorise metal reactivity. You're not expected to just only use a periodic table. You will be given a separate table, which will be at the end of the exam, and so you can sit that there and you can use that to work out reactivity. It's a reactivity series table. Okay. Recognise trends in reactivity of a selection of metals. Recognise the trends in reactivity. Oh, I've written that twice. That's a bit silly. So I can fix that. And those are your standard terms and definitions. So it's actually fairly straightforward. Now, you've seen compounds before. It's a pure substance made up of two or more different types of atom, chemically bonded. Okay. Now, when we talk about ores, what do we mean? Okay. For example, gold has been known for thousands of years. You know, in ancient cultures, gold and silver as well, and platinum. But iron wasn't discovered and worked with until the Iron Age. It's comparatively recent. And why is that? Well, iron is not found as a pure element. You won't find a lump of iron sitting on the ground. Okay, it would rust away if it was in that configuration. Iron is only found as an ore, bound to something else. So here we have hematite, magnetite, siderite, pyrite. In each case, you can see the iron is sitting there. So iron is not found in nature as anything other than an ore, and therefore it has to be smelted out. Whereas gold, because it's exceptionally unreactive, can be found in its free form, in its free state. It won't rust, it won't break down. It won't decompose if exposed to air or to water. But more reactive metals do decompose in air and water. Lithium, for example, have you ever seen lithium in water? Did a teacher show you that maybe in year 8? Lithium in water will bubble, fizz, hydrogen gas is explosively given off. It may even burn. So obviously you're not going to find lumps of lithium in nature because they will be exposed to water almost immediately, and that will happen. They'll decompose. But gold is lithium highly reactive, gold completely unreactive. So that, a lump of gold sitting outside for 10,000 years will remain a lump of gold. It will be just fine. And that comes down to its reactivity as well. Okay. So when the earth formed, the more reactive metals, including aluminum, copper, zinc and iron, reacted with other elements to form ionic compounds. And these are ores, so it's an ionic bond. Okay. Iron ores include, these are some examples here. You don't need to memorise iron ores. The key point to take away from this is the more reactive metals will only be found as an ore in nature. You'll never find them just sitting as a pure element. metals is dependent on how easily they're able to give up their outer shell electrons. And there you go. So we're seeing that pattern again. If you're reactive, you give up those outer shell electrons very easily. Unreactive metals don't give up their valence shells electron easily. It's the same thing we've seen before. So that's a key point there. And the general overall point is, if the metal is unreactive, it's probably been known about for thousands of years, because you could just find it just sitting in nature. But if it's very reactive, you will not get anything other than an ore, and that needs to be smelted. As I said, it needs to be melted out and then collected and purified, and then you can work with it. Okay. Now, any questions about that? Yes?
So when you say give up their valencing electrons,
yes.
like actually give up, like in ionic bonding?
Yeah, so there could be ionic bonding forming and things like that, yeah. So metals will often donate electrons.
Yeah.
Okay, now, any other questions about this? Can I change? As I said, that's really the key point there. There's two key points. One is, reactive metals aren't easily found in nature because they decompose. Unreactive metals are found in nature and have been known about for thousands of years because they don't decompose or react. And it comes down once again to valence electrons. It's that same point repeated again and again. Valence electrons. Okay. Now, here's displacement. And this is iron. So iron metal, here is copper sulfate, and in an aqueous solution. And you can see what is formed at the end is iron sulfate. The iron displaces, is more attractive in a bond for the sulfate than the copper is. So the iron displaces the copper, and you end up with a salt, iron sulfate, and pure copper metal. And where does that pure copper metal go? I've got a little slide, but what it'll actually do is, so I have a little slide, maybe on the next slide, where you put an iron nail into copper sulfate, and it seems to grow a rust-like fur all over the iron nail, and that is actually the copper binding to the iron as well. It's sticking to the iron nail, but this is floating in the solution. So we'll have a look at exactly that equation again. I think it's on the next slide. It's very close. Okay. In this example, iron has displaced copper from the copper sulfate solution. The reactions of metals with acids are examples of displacement reactions. And your job at this level is, if I gave you that equation and a reactivity table, your job will be to say, is a reaction going to occur? And so you'll have to look at the metals to see which one is more reactive, is more attractive to the sulfate, because that's the one that the sulfate will go to. And if a reaction does occur, you'll need to complete the equation, and it will need to be a balanced equation. And we haven't really done balancing chemical equations. Again, that's done in Year 9. We might have a bit of time before the test to do that. I've sort of planned far enough ahead to allow a revision class on balancing chemical equations. But just quickly, is that equation balanced? How can I tell? What do I look for in a balanced equation? Same amount on either side of the arrow. So how many ions do I have here? One. How many ions over here? One. How many copper? One. How many copper? One. Sulfate? One sulfate, so we're okay. So we're fine. Okay. So that would be exceptionally easy to balance that equation. Okay. Now can I change? What? What are you writing down? See, I don't know, on this side you could potentially put a little arrow to show that the sulfate is going to migrate over here. Or you could say that iron literally will displace the copper. It will form a salt that is more attractive to the sulfate than the copper was originally. Okay. Okay. Now, let's have a look at this. Okay, same equation, same information. You don't need to write that down again. And what's happening here? So, copper sulfate is blue, is the blue solution. But iron sulfate, this one here, is colourless. And you'll notice the blue solution at the start, where are we? Blue, and it slowly becomes colourless as this compound is formed. And the copper is actually the orange thing accumulating on the iron. And that's what's happening there. Part of one reactant is replaced by another reactant. The more reactive metal displaces the less reactive metal, and often one metal is deposited on another metal. The pure copper metal is deposited on the iron nail. So the iron nail is breaking down a little bit for this to occur, this to be formed, and the copper metal is being deposited on the iron nail. And that is exactly, what's happening there. Okay, obviously sped up many, many times over. Now, can I change? As I said, that information is identical to what you had there, as is the equation, the chemical equation. Put your notes. Better keep up. We're doing a crack on this. We're doing a crack precisely on this. Okay. Now, a term that came up a couple of exams ago was ionisation energy, a measure of how easily atoms lose electrons and become positive ions. And so, if you have, essentially in terms of reactivity, on the periodic table, where are the most reactive elements found?
Bottom
left.
The most reactive are in the bottom left, and the least reactive are in the top right of the periodic table. And that's what's reflected here, because it's a reflection of atomic radius and metallic properties that increase along that. Where is ionisation energy? So the elements on the top right of the periodic table have high ionisation energy. They don't give up electrons easily, or rather, it would take a lot of energy to steal the electrons from them. You would need a lot of energy for that to occur, for them to form an ion. Whereas the elements at this part of the periodic table have low ionisation energy. Just a little bit of energy is enough for the valence electron in the group 1 to be stolen away. Okay, you follow that idea? Lots of energy, a little bit of energy needed to steal an electron, lots of energy needed to steal an electron. So on your periodic table, you could write that as well. If you've got your periodic table here, you can put in this corner here, lots of energy needed to steal an electron, a little bit of energy needed to steal an electron. Okay. So, top right, high ionisation energy. Look at the periodic table. Another one. That's the solution. Write that down and put a note to yourself that I'm going to, on my periodic table, put this information and everything else. So you're going to have to copy a close personal friend. Yeah, bottom left is low ionisation energy. Not much energy needed to steal electrons. Top right, high ionisation energy. Lots of energy needed to steal electrons. If you want to take an electron off fluorine, it's going to fight you for it. It's really, really small radius, so those electrons are very strongly attracted to the protons. Very difficult to extract. Okay. Yes?
Do you oppose the periodics on that?
No.
Is that even possible to steal an electron from here?
Oh, look, you put enough energy into anything and you'll get the job done.
What about the hydrogen?
Sorry? What would happen to if you stole its electron? It'll donate that sometimes. Then it's a proton. Alex has just asked me a question about hydrogen. What happens if hydrogen loses an electron? Isn't that what an acid is? Isn't an acid from year 9 and basically a proton donor, or it has H plus ions in solution, Jacob. That is effectively hydrogen in HCl in solution is hydrogen ions and chlorine ions. Okay? And isn't H plus basically a proton? It is a proton. It has no electrons. And how attractive is a raw proton to electrons? It is massively attractive to them. So what would happen, I'm sure I went through this with you guys, what would happen if I dumped a bucket of just exposed protons onto the back of your hand? Well, those protons are going to pull electrons out of your skin, and effectively that's what's happening with an acid. Why are acids corrosive? Why do they break things down? They're stealing electrons, and I need my electrons to hold my skin together. That's what's happening at the level of atoms. Okay, that's why acids are corrosive. And the more corrosive an acid is, the more it has of these in solution. Vinegar only has a few of these floating around, so you get some in your eye and it's, ow, that's painful. But on the back of your hand, yeah, it's not.
It's stealing your eye electrons.
No, it's just sort of chemically burning them. It's just kind of hurting. But it's probably taken a few, but you're okay. That happens all the time. Remember, you're losing stuff all the time and you're rebuilding your stuff all the time. So don't freak out. The very concentrated acid is considerably worse. Considerably worse. And a base is the opposite. Okay, that's sort of a little bit of insight on acids. We don't do that. Chelsea's law. A student a few years ago, this was the only way that resonated with her on what is happening reactivity of metals. The reactive bullies, like zinc, steal the girlfriends of less reactive metals or geeks. So lithium is, some kind of Italian god in terms of his attractiveness to girls or to metals. Gold is the ultimate geek. It is completely unattractive in every possible way. Gold is quite happy spending alone time. And that's effectively, and that's the table you'll be given. And look there, hydrogen, which of course you consider to be a gas, does act like a metal. Okay? And what you should note here also is these ones here will react vigorously with cold water to form hydrogen gas. So these will give off hydrogen gas with just in the presence of water. So if you drop lithium in water, it will bubble, and those bubbles are hydrogen gas. Now react with steam to form hydrogen gas, so a little more energy is needed in the form of steam, all the way down to iron. React with acids to form hydrogen gas, and then will not dissolve in simple acids. And so that's fundamentally what's happening here. So on this one, increasing ease of oxidation, what does all of this mean? Up the top, most reactive, down the bottom, least reactive. And you'll get something like that on both the test and the exam. And you might be given a few equations and you'll need to look and you'll go, oh yeah, what are the two metals? I'll need to identify the two metals. Where are they found in the chemical equation? They're always in front. And then if, say, lithium is present and lead is present as a compound, lithium will steal whatever lead is attached to. It is much more attractive to whatever lead is attached to, and we'll just take that. It will displace lead in a reaction. Okay? So where is copper here? Here's copper. Where is iron? Here. Which metal is more reactive? Put up your right hand if you think iron. Put up your left hand if you think copper. Iron, if you think iron is most reactive, put up your right hand. If you think copper, put up your left hand. And you're right. Iron is most reactive. So, in that reaction, which one is most reactive? Iron. Iron is more reactive than copper. So, iron displaces the copper. That's what's happening here. That's in the form of the chemical reaction. That's in the form of example. That's precisely what's happening there. And that free-floating copper has got a light charge on it, so it will stick to the iron in the nail, and off it goes from there. Okay. Now, much simpler in a table to just do a comparison. Okay, unreactive elements, the geeks if you like, reactive elements, the bullies. They form stable compounds because they don't want to react with things. Gold and silver occur as free elements in nature. Others form easily decomposed. Oh, sorry, the compounds are unstable. Not thinking straight. The compounds are unstable. They don't hold on to whatever, their girlfriend if you like, very strongly. Okay, and you can flip it around if you like. And so they form unstable compounds. They are easily decomposed. Okay, they are easily displaced. Copper, lead and tin are metals which are easily extracted from their ores, and they are very reactive metals. Because they're reactive, so they do form compounds in nature, but you can pull them out pretty easily. Not much energy is required. The least reactive metals have been known for many thousands of years. Gold, for example, as I mentioned, you can find it on the ground. It doesn't break down, it doesn't react with air, it doesn't react with water. It can just sit there. Now, the opposite, at the opposite end of the spectrum, like lithium, the reactive elements, the compounds are very stable. They really, once they form a compound, they really hang on to it. They exist naturally only as compounds and not found as free elements. Their compounds do not decompose or break down easily. Like iron ore, the iron in that iron ore doesn't decompose easily. It's a very, very stable compound. To get it out of there, you'll need a lot of energy. You will need to smelt the iron out. Not easily extracted, have only been known for a few hundred years. Okay? Just thought of something. I just thought of something which will wake you up. Now, I'll leave that on there. Does anyone have any questions? Okay, I've got the video.
What's your girlfriends?
Huh? Oh, see, now you're thinking, you're probably overextending that metaphor. Okay. Oh, well, they're the non-metals. It can be any non-metal, or it can be an ionic compound. Okay, sorry, covalent compound. Have a look at this quick. There. SO4. Is SO4 ionic, or is it covalent? Bring out your periodic table of ions. Covalent. Is that a non-metal? Is that a non-metal? But this is ionic. So look, this is another thing. Mr. Waldron, he's lying in wait. He's sitting there even now in his fortress of solitude, typing up the Year 10 exam. He leaves the chemistry. I have literally received SMS messages from Mr. Waldron on the weekend going, I'm reading the most fascinating article about some gold compound in a cafe. Okay, so now have a look at your ionic, that's the one. Have a look at that. Where is sulfate there? Look at the box. It should have a red dot beside it. What? You see sulfate? What charge does it have on it? SO4. It's got a 2 minus. So SO4 has a 2 minus charge, and very importantly, is sulfur and oxygen, the bond there, ionic or covalent? Well, are they metals or non-metals? They're non-metals, so you are correct. That is a covalent bond, right? Now, that's got a 2 minus charge, ergo, copper must have a 2 plus charge. It's an electron donor. Yes, it's a metal, it donates electrons. And is the bond here, between these two, ionic or covalent? Ionic. That's an ionic bond there. That's a covalent bond there, recognised by the non-metal. As I mentioned to you before, did anyone write that down? It would be a really good idea. All of these compounds, all of them, covalently bonded. Every single one of them. If you look, every single one of them is non-metal, 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 non-metal. They are all covalent bonds. So if in an exam situation, if you were shown that copper sulfate and you were given the option of is that molecule ionic bonding, covalent bonding, or both, the answer would be both. Because that component as a polyatomic ion is covalent bonding. That component there is ionically bonded. Okay? And so we got into this because Alex asked a pretty good question. And iron itself, in this case, forms a 2+. Iron here has gotten rid of a couple of electrons and is more attractive to the sulfate than the copper is. And so it displaces. And if you had to bet money, if you were looking at iron and you were looking at copper, which do you think would have a greater atomic radius, would be the bigger, or have the valence shell farthest from the protons? Or another way, the distance from the valence electron to the protons had the smallest distance. So those attractive protons that are going to attract that negative charge, which one do you think would have the shortest distance between the protons and the valence shell? It would be iron. And that is what, yeah, see Lewis is doing laps at the back. It would be iron and that is why it's more attractive to this. And it'll get it. It'll pull it off. Okay? And that's it, because that negative charge wants protons. And the protons here are closer than the protons here. Just pulls it off. Yes?
How does the sulfate get a negative charge in the first place?
Well, if you draw out the molecule, okay, so we don't really expose you to, in terms of covalent bonds, to anything that's not balanced. You understand? So we're pretty gentle at a year 10 level. We say, here are some polyatomic ions and they have a charge, and we never get you to draw that out as a structural diagram. But if you did so, you would need to have extracted. If you do so, to get the structural diagram to demonstrate that. I won't draw it out now, but I might come and see you after I get everyone else started. But yeah, you've got your 4 oxygens and you've got your sulfur, and in order for that to form that molecule, you'll need to eject 2 electrons from the mix, and you'll get that. But we don't, at this level, construct those. We're quite happy if you can identify ionic, covalent, draw some structural diagrams, be able to work with hydrocarbons and with reactivity of metals. And that, by the way, that copper 2, what do you think that 2 refers to? The charge. Yeah? And so what is that one? Would that be iron 2? Yeah. And it can form iron 3 as well. Okay? So the little subscript number, that little number there, is a reflection of charge. Okay? So, I think... Oh yeah, little video for you.
Yes.